The work Discrete breathers and negative temperature states has been done by Stefano Iubini, Roberto Franzosi, Roberto Livi, Gianluca Oppo and Antonio Politi, in a collaboration among the universities of Florence in Italy, Strathclyde and Aberdeen in the United Kingdom, and the CNR in Sesto Fiorentino in Italy. First of all, we want to clarify the meaning of negative temperatures by considering an ensemble of two-level atoms, where the total internal energy is bound. In the minimum energy state, all the atoms are in the ground state. Since this state is perfectly ordered, its entropy is zero. But so is the entropy for the maximum energy state, where all the atoms are in the excited state. This means that if we plot the entropy S as a function of the internal energy U, we obtain a curve with at least one maximum value. Since the temperature T is the inverse of the slope of this curve, we observe on the left side of the picture positive slopes corresponding to positive temperatures. At the maximum, a zero slope where we have infinite temperature, and on the right of the picture negative slopes and negative temperatures. This means that negative temperatures are extremely hot and above the infinite temperature point. This does not in any way violate the absolute zero temperature introduced by Lord Kelvin. In this paper, we study negative temperature states in the discrete nonlinear Schrödinger equation. This equation describes accurately Bose-Einstein condensates in a deep optical lattice, but also arrays of coupled optical waveguides. The hopping term describes either the tunneling effect of the BEC in the optical lattice or the coupling among the waveguides. It is important to note that in the discrete nonlinear Schrödinger equation there are two conserved quantities, the total energy and the total atomic density. It is possible to provide a statistical mechanics description of the solutions of the discrete nonlinear Schrödinger equation, as displayed in this diagram where we report the energy density versus the particle density. There exists a line of infinite temperature in red separating a region of negative temperatures from a region at positive temperatures. The main question addressed in our work is: can we access the region at negative temperatures? On the right, we see the temporal evolution of two different realizations above the infinite temperature line. In both cases, we observe the formation and annihilation of discrete breathers that are highly spatially localized states corresponding to large values of the particle density in just a few lattice sites. By increasing the size of the lattice M, we also observe that the density of breathers approaches a quasi-stationary value corresponding to an interbreather distance of around 900 lattice sites. The presence of many discrete breathers in the quasi-stationary state at negative temperature is displayed in this animation. The breather density ρ approaches a final value that is independent of the initial condition, and so does the inverse of the temperature beta that converges towards negative values measured by a suitable microcanonical thermometer. It is possible in the discrete nonlinear Schrödinger equation to move from positive to negative temperatures without artificial changes of the sign of the energy. By following a method introduced by some of us in 2006, one can remove particles and energy at the boundaries of the lattice and progressively move across the line of infinite temperatures. In conclusion, we have demonstrated that negative temperature states with discrete breathers should be experimentally realizable in BEC in optical lattices and large arrays of optical waveguides. It is possible to move from positive to negative temperatures by free expansion of the BEC on a larger lattice or by removing particles and energies from the boundary. These methods do not rely on artificial changes of the sign of the total energy. Simply marvelous.